If f is the function whose graph is shown, and the function a of x is defined to be the definite integral from 0 to x, f of t dt. Find the values of a of 0, a of 1, a of 2, a of 3, a of 4, and a of 5. Then sketch the rough graph of a by first plotting points. The function a of x is defined to be the definite integral, which geometrically represents the area between the curve and the horizontal axis. The function a of x is defined so that the lower limit is always 0 and the upper limit is whatever the input of the function a. Because of this, a of 0 is the integral from 0 to 0, f of t dt, and this is 0 because there is no width here, going from x equals 0 to x equals 0. A of 1 is the definite integral from 0 to 1 of f of t dt. This is the graph of f, and so from 0 to 1, the area between the curve and the horizontal axis is the area of this triangle with the base 1 and the height 2. The area of that triangle is 1/2 base times height, and this is 1. A of 2 is, by the definition, the definite integral from 0 to 2, f of t dt. This is the area under the curve from x equals 0 to x equals 2. This area, we can compute it in two different ways. We see that this area is 1, and the area between 1 and 2 is 2. Each of the square has an area of 1, and there are two squares between 1 to 2. And so, a of 2 is 3. Another way to see this is we can rewrite this as the integral from 0 to 1 f of t dt plus the integral from 1 to 2 f of t dt. And again, we computed the integral from 0 to 1 already, and it is 1. And the integral from 1 to 2 is the area between the curves and the horizontal axis, and we see that that is 2. And so a of 2 is 3. A of 3, by the definition, is the integral from 0 to 3 f of t dt, and this is the integral from 0 to 2 f of t dt plus the integral from 2 to 3 f of t dt. But we found that the integral from 0 to 2 f of t dt is already 3, and the integral from 2 to 3 f of t dt is the area under this curve above the x-axis. To approximate the area, we can count, or a better word, we see how many squares we can fit in this curve. We see that for the bottom half, it is not quite a square yet, not quite one square, the area under the curve, but there is almost half a square for the top part. And so both of these add up to be more than one squared, and we approximated that is almost 1.2 or 1.3. And so we estimate that a of 3 is about 4.3. Using symmetry, we can estimate a of 4. A of 4, by the definition, is the integral from 0 to 4 f of t dt, and we can separate this at the integral from 0 to 3 f of t dt plus the integral from 3 to 4 f of t dt. But the integral from 0 to 3 f of t dt is 4.3. We estimated in the previous step. From 3 to 4, the curve is below the x-axis, and so this integral will be negative. The integral represents the signed area, if the curve is above the x-axis, the area is positive, and if the curve is below the x-axis, we end up with the negative of the area. And using symmetry, if the area from 2 to 3 is roughly 1.3, then the area or the signed area from 3 to 4 is negative 1.3. So we would add negative 1.3, and so we end up with 3. A of 4 is 3. And lastly, A of 5, by the definition, is the integral from 0 to 5, f of t dt. And we split this integral again. This is the integral from 0 to 4, f of t dt, plus the integral from 4 to 5, f of t dt. And the first integral is 3 plus 2. Again, using symmetry, this area between the curve and the x-axis is negative 1.3. So this is roughly 1.7. 3 minus 1.3 is 1.7. To sketch the graph of the function a, we will summarize the result from the computations. When x equals 0, a of 0 is 0. When x equals 1, a of 1 is 1. When x equals 2, a of 2 is 3. When x equals 3, a of 3 is 4.3. When x equals 4, a of 4 was 3. And when x equals 5, a of 5 is 1.7. To sketch the graph of a, we first need to plot these points because these points satisfy the function a. We will plot the graph of a below the graph of f of t so that we can compare the two results. Since these points satisfy the function a, we plot them when x equals 0, y equals 0, 1 point. When x equals 1, y equals 1. When x equals 2, y equals 3. When x equals 3, y equals 4.3, a bit above 4. When x equals 4, y equals 3, or a equals 3. And when x equals 5, a equals 1.7. We also see that the graph of f of t is above the x-axis from 0 to 3, and that the graph of a is increasing from 0 to 3. The graph of f of t is below the x-axis from 3 to 5, and that the graph of a is decreasing. Also, the graph of f of t is increasing from 0 to 1. Not only it is above the x-axis, but it is also increasing. And so from 0 to 1, the graph of a will be increasing concave up. From 1 to 2, the graph of f of t is above the x-axis and it is flat. And so the graph of a will be increasing at a constant rate. From 3 to 4, the graph of f of t is above the x-axis and it is decreasing, and so the graph of a will be increasing and concave down. From 3 to 4, the graph of f of t is below the x-axis and it is decreasing, and so the graph of a will be decreasing and concave down. From 4 to 5, the graph of f of t is below the x-axis, so a will be decreasing, but since f of t is increasing, the graph of a will be concave up, decreasing. And this is the graph of a of x. Compare this to the graph of f of t. We see that this is an antiderivative of f of t.